Picture this. You're floating in the vast emptiness of space, weightless, surrounded by an ocean of galaxies stretching infinitely in every direction. The silence is absolute, yet the universe is alive with motion. Stars are being born in brilliant nurseries of gas and dust, while others are dying, collapsing into dense neutron stars or vanishing into the abyss of black holes. Planets orbit their suns, moons dance in cosmic harmony, and somewhere, hidden beneath all of this, beneath the very fabric of reality, something deeper might be at play. Not atoms, not subatomic particles, but tiny vibrating strings, invisible yet fundamental, weaving the structure of the cosmos itself. This is string theory, an idea so radical, so all-encompassing, that if proven true, it could unify our entire understanding of the universe. But here's the problem: it has never been proven. It has remained an elegant, almost poetic framework of mathematics, lacking the experimental evidence needed to transform it from a beautiful idea into a scientific revolution. Decades have passed, and string theory has remained a puzzle that physicists can't quite solve. But now something has changed. A new discovery, one that we'll explore soon, could provide the first tangible proof that these tiny strings are not just theoretical constructs, but real, physical entities. If confirmed, this would rewrite the laws of physics, force us to rethink space and time, and perhaps even reveal hidden dimensions that have been right in front of us all along. To understand why this is such a big deal, we need to go back, way back, to the foundations of physics itself. For centuries, scientists believed that matter was made up of tiny, indivisible units. The ancient Greeks called them atoms, believing they were the smallest building blocks of existence. But as science advanced, we discovered that atoms were not indivisible at all. They had a nucleus packed with protons and neutrons, surrounded by a cloud of electrons. And as we probed even deeper, we realized that even these protons and neutrons weren't fundamental. They were made of something smaller, quarks, held together by an invisible force carried by particles called gluons. This led to the development of the standard model of particle physics, a breathtakingly successful framework describing all known particles and forces, except one. The one force that refused to fit into this picture was gravity. While the standard model explains electromagnetism, the weak force, and the strong nuclear force, it simply doesn't account for gravity at the quantum level. And that's a huge problem. Albert Einstein's general relativity describes gravity as the bending of space-time, and it works perfectly at large scales. It explains the movement of planets, the warping of light around massive objects, and even the expansion of the universe itself. But when you try to apply general relativity to the subatomic world, where quantum mechanics reigns supreme, the equations break down. Gravity refuses to play by the same rules as the other forces. This is the great divide in physics. On one side, quantum mechanics governs the tiny, atoms, quarks, photons. On the other, general relativity governs the immense, planets, galaxies, black holes. But the universe doesn't have two sets of laws. It has one. And we don't know what it is. String theory emerged as a possible answer. Instead of treating particles as tiny, point-like dots, it proposes that everything is made up of unimaginably small, vibrating strings. The frequency at which a string vibrates determines what kind of particle it becomes. A particular vibration might create an electron, another might create a quark, and yet another, a graviton, the hypothetical particle responsible for carrying gravity itself. If this is true, then gravity is not separate from the other forces. It's just another vibration of the fundamental strings, and string theory naturally unifies all forces of nature into a single framework. It's an astonishing idea. But there's a catch. For string theory to work mathematically, our universe must have more than just the three spatial dimensions we experience. It requires additional dimensions, 6 or 7 extra dimensions, curled up so tightly that they remain hidden from our perception. Imagine an ant walking on a tightrope. To us, the tightrope looks like a simple one-dimensional line, but to the ant, the tightrope has depth. It can move forward, but it can also move around the rope's surface in a second, unseen dimension. String theory suggests that similar hidden dimensions might exist all around us, too small for us to see, but crucial to the very structure of reality. This is where skepticism arises. No one has ever observed these extra dimensions. No experiment has ever directly detected a string. String theory's mathematical beauty is undeniable, but in science, beauty isn't enough. A theory must be testable. It must make predictions that can be confirmed or falsified by experiments, and for decades, string theory has struggled with that final step, turning its equations into real-world observable proof. Some physicists have gone so far as to say that string theory isn't a scientific theory at all, but rather a mathematical framework, a kind of pre-theory waiting for evidence. Without experimental confirmation, it has remained trapped in a limbo between genius and speculation, but all of that might be about to change. A recent breakthrough, one rooted in real, physical observations, has suddenly breathed new life into the search for proof. It may not show us the strings themselves, but it might provide the first experimental evidence that the hidden dimensions predicted by string theory actually exist. If confirmed, it would be the first real step toward proving that string theory isn't just a beautiful idea, it's the true nature of reality itself. But before we dive into this breakthrough, I have a quick request. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Now, what exactly is this breakthrough? Could it finally provide the first direct evidence of hidden dimensions? And if it does, what does that mean for the universe? Imagine you're in a vast, high-tech underground laboratory, surrounded by the hum of superconducting magnets and the faint vibrations of machinery operating at temperatures colder than deep space. This is CERN, home of the Large Hadron Collider, the most powerful particle accelerator on Earth. It's here, beneath layers of concrete and steel, that physicists smash particles together at nearly the speed of light, hoping to unlock the deepest secrets of the universe. In 2012, this is where the Higgs boson was discovered, a particle so fundamental that without it, matter as we know it wouldn't exist. But now something even more profound may be within reach, something that could finally provide the first testable evidence of string theory. For decades, physicists have searched for a way to experimentally probe the predictions of string theory. One of the most promising avenues has been the hunt for extra dimensions, the hidden spatial dimensions that string theory requires to function. But how do you detect something that exists beyond the three familiar dimensions of length, width, and height? The answer lies in the energy of particle collisions. According to string theory, if extra dimensions exist, then under the extreme conditions of a high-energy collision, like those created in the Large Hadron Collider, some of the energy might leak into these extra dimensions, effectively vanishing from our visible universe. The result? Particles in the detector would suddenly appear to carry less energy than they should, as if a portion of that energy had slipped away into an unseen realm. Scientists call this the search for missing energy events, and for years, they've been combing through collision data looking for unexplained energy loss. Recently, hints of such energy discrepancies have started to emerge. While still not conclusive, they suggest that something beyond the standard model might be at play. Could this be the first indirect proof that extra dimensions exist? If so, it would be a game changer. It would mean that string theory isn't just an abstract mathematical exercise. It's describing something real, something woven into the very fabric of the cosmos. But the Large Hadron Collider isn't the only place where evidence for string theory might be lurking. Some of the strongest clues could actually come from the most extreme objects in the universe, black holes. Black holes are nature's ultimate laboratories for testing the limits of physics. They are so dense, so powerful, that they warp space and time to the point where nothing, not even light, can escape. Einstein's general relativity predicts their behavior with stunning accuracy, but when we try to apply quantum mechanics to black holes, contradictions arise. According to quantum physics, information can never be destroyed, but if something falls into a black hole, general relativity suggests that information is lost forever. This is known as the black hole information paradox, and for decades, it has been one of the greatest unsolved mysteries in physics. String theory might hold the answer. One of its most profound predictions is that black holes are not just infinitely dense points of matter, but instead they have a hidden underlying structure, possibly made up of vibrating strings. If this is true, it would completely change our understanding of what happens inside a black hole. Instead of information being lost forever, it might be stored in a way we haven't yet comprehended. Astrophysicists are now using advanced telescopes, including the Event Horizon Telescope, the same instrument that captured the first ever image of a black hole in 2019, to search for subtle hints that string theory's predictions about black holes might be correct. If we find deviations from general relativity in the behavior of black hole event horizons, it could be the first observational proof that strings are the fundamental building blocks of reality. But there's another way string theory could be tested, one that doesn't require smashing particles together or peering into black holes. Instead, it involves something much more bizarre, something that exists all around us, yet remains one of the greatest mysteries in physics: dark matter. Dark matter makes up about 85% of the matter in the universe, yet we don't know what it is. It doesn't emit light. It doesn't interact with regular matter in any obvious way, and it only reveals its presence through its gravitational effects on galaxies and cosmic structures. But here's where things get interesting. String theory predicts the existence of new particles, including one called the axion, a hypothetical particle that could explain dark matter. If axions exist, they might be detectable through their interaction with electromagnetic fields, meaning that with the right kind of experiment, we might finally uncover their presence. At several underground laboratories, including the Axion Dark Matter Experiment ADMX in Washington State, scientists are hunting for these elusive particles. They are using ultra-sensitive detectors cooled to near absolute zero, scanning for tiny fluctuations in electromagnetic fields that might betray the presence of axions. If detected, it would be a major victory for string theory, providing real-world evidence that its predictions extend beyond elegant mathematics. Right now, we stand at the edge of an incredible moment in science. From high-energy particle collisions at the Large Hadron Collider to black hole observations and dark matter experiments, we are closer than ever to putting string theory to the test. The next few years could determine whether it remains a beautiful but unprovable idea, or the most important discovery in physics. But what happens if string theory is proven? If the universe is indeed made of tiny vibrating strings, and if extra dimensions truly exist, how would that change our understanding of reality itself? The answer is even more mind-bending than you might think. And that's exactly what we'll explore next. Imagine waking up one day to a news alert that changes everything. Scientists at CERN have just announced an earth-shattering discovery. Evidence that the universe is not made of point-like particles as once believed, but of tiny vibrating strings. The implications are staggering. Suddenly, the idea that our reality is far richer and more complex than we ever imagined is no longer science fiction, it's science fact. But what would that actually mean for us? To understand the impact, let's take a step back and consider how past revolutions in physics transformed the way we perceive the universe. In the early 20th century, Albert Einstein's theory of relativity shattered the Newtonian view of space and time as fixed and absolute. Instead, he revealed a universe where time slows down near massive objects, space itself bends under gravity, and nothing, not even light, can travel faster than a cosmic speed limit. Decades later, quantum mechanics upended our understanding, again, showing us a reality where particles can exist in multiple states at once, where objects can be entangled across vast distances, and where the very act of observation can alter reality. Each of these discoveries didn't just reshape physics textbooks, they changed how we understood existence itself. Now, string theory stands at the brink of becoming the next great leap. If proven true, it wouldn't just be another incremental discovery. It would be a paradigm shift as monumental as relativity or quantum mechanics. But what would it actually tell us about the universe? One of the most mind-boggling implications of string theory is that reality might not be limited to just the 3 dimensions of space and one of time that we experience. Instead, there could be additional dimensions curled up in microscopic shapes so small that they escape our direct perception. Imagine a 2-dimensional world painted on a piece of paper. To the beings living on that paper, their universe is flat and they can move left, right, forward and backward, but never up or down. Now imagine lifting that piece of paper into the air. To us, the 3rd dimension is obvious, but to the beings on the paper, it would be completely invisible. What if we are just like those 2-dimensional beings, trapped in a 3-dimensional perception of reality, while extra dimensions exist all around us, just beyond our grasp? According to string theory, these hidden dimensions might be folded into intricate, compact shapes called Calabi-Yau manifolds, tiny geometric structures that exist at the smallest scales imaginable. If we could somehow access these extra dimensions, it could unlock possibilities far beyond what we ever considered possible. For instance, gravity, which appears weak compared to the other fundamental forces, might actually be leaking into extra dimensions, explaining why it's so much weaker than electromagnetism or nuclear forces. This could even lead to mind-blowing technological applications. If we could manipulate gravity at a quantum level, could we one day create artificial gravitational fields? Could we harness the physics of extra dimensions to develop propulsion systems beyond anything currently possible? And then there's the question of the multiverse. String theory doesn't just allow for multiple universes, it practically demands them. The mathematics suggests that our universe is just one of many, possibly an infinite number, each with its own laws of physics. Some might be wildly different from ours, with entirely different physical constants, while others might be eerily similar, possibly containing alternate versions of ourselves. If we ever find a way to experimentally confirm this, it would mean that everything we know, the entirety of human history, the stars in the sky, the galaxies beyond, might be just a single drop in an endless cosmic ocean. But how could we ever prove such a thing? It turns out scientists are already working on it. Cosmic microwave background radiation, the afterglow of the Big Bang, might contain subtle imprints of interactions with other universes. Some researchers have proposed that if our universe has ever bumped into another in the distant past, the collision might have left detectable scars in the fabric of space-time. Future telescopes, far more advanced than anything we have today, could one day scan the cosmos for these telltale signatures. If found, it would be the first direct evidence that we are not alone, not just in terms of life, but in terms of entire realities. Of course, not everyone is convinced that string theory is the ultimate answer. Critics argue that without experimental confirmation, it remains a mathematical abstraction, a beautiful but untestable idea. Some physicists, like Nobel laureate Roger Penrose, argue that alternative theories such as loop quantum gravity, which attempts to explain gravity at the quantum level without extra dimensions or strings, might provide a better answer. Others question whether string theory's reliance on extra dimensions is an unnecessary complication rather than a true reflection of reality. Yet, despite the skepticism, string theory remains the most mathematically elegant and unifying framework we have ever conceived. And if the latest experiments continue to uncover hints of extra dimensions, missing energy events, or even the elusive axions predicted by the theory, we might be on the verge of proving once and for all that the fabric of reality is far stranger and more fascinating than we ever imagined. But if string theory is true, what's next? Could we one day manipulate the very strings of the universe to engineer reality itself? And how might this discovery challenge not just our understanding of physics, but the very way we see ourselves in the cosmos? If string theory is right, if the universe is woven from infinitesimally small vibrating filaments, then reality is not made of particles, but of pure resonating energy. That means at its core, everything we see, touch, and experience is just different notes on an unimaginably vast cosmic symphony. But here's the real question. If we could understand the strings, if we could tune them, what would that mean for the future of humanity? For centuries, our technological progress has been driven by our understanding of physics. When we unlocked the laws of motion, we built machines. When we mastered electromagnetism, we created electricity, radio, and the internet. When we harnessed quantum mechanics, we entered the age of semiconductors and computing. But if string theory is proven, and we learn to manipulate the very fabric of existence, our potential might be limitless. Imagine a world where we don't just observe the fundamental forces, but actively control them. The physics of strings suggests the possibility of altering the constants of nature. What if we could adjust the strength of gravity, making space travel far easier? What if we could control electromagnetism at its most fundamental level, making wireless power transmission and quantum-level computing trivial? If string theory is right, we may one day build technologies beyond anything we can currently imagine. Technologies that don't just operate within the laws of physics, but redefine them. And then, there's the question of extra dimensions. If these hidden layers of reality truly exist, how might we interact with them? Could we, with advanced enough engineering, create pathways, gateways, to higher dimensional spaces? It's been speculated that if these extra dimensions are accessible, they might offer entirely new methods of transportation, perhaps even instantaneous travel between distant points in space. If gravity is already leaking into these dimensions, could we find a way to manipulate that leakage, bending space in ways previously thought impossible? Some physicists have suggested that this could lead to real-life warp drives, bypassing the need for traditional propulsion by literally reshaping the space between 2 points. But let's go even deeper. If string theory's multiverse prediction is correct, then our reality is not unique. There could be other universes, parallel dimensions, alternate versions of history, maybe even alternate versions of us. What if one day we could reach across the cosmic divide? Could advanced civilizations in other universes have already figured this out? The implications are staggering. String theory, if true, does not just change physics. It redefines our place in existence itself. Of course, with great discoveries come great existential questions. If our universe is just one among many, then what makes it special? Is there a deeper reason why these specific laws of physics govern our reality? Or is it simply one of infinite possibilities? And if strings are the foundation of everything, where did they come from? Are they eternal? Were they created? Could they themselves be part of an even deeper structure we have yet to uncover? The search for truth is never-ending, and string theory, whether ultimately proven or refined into something even greater, represents humanity's most ambitious attempt to unify everything we know. Right now, experiments at the Large Hadron Collider are searching for evidence, signs of extra dimensions, traces of new particles, hints that strings are more than just elegant mathematics. And while the answers may not come tomorrow, every step we take brings us closer to unlocking the true nature of the universe. But now the question is for you. If string theory is right, if everything is connected by vibrating cosmic threads, what does that mean for consciousness? For free will, for the meaning of existence itself? Could we one day use this knowledge to reshape reality? Or are we merely spectators in a cosmic concert beyond our control? One thing is certain. The universe is far stranger, far richer, and far more mysterious than we ever imagined. And the deeper we go, the more we realize we've only just begun. If this video made you think, share your thoughts in the comments. What excites you most about the possibilities of string theory? Could it lead to new technologies, new understandings, or even a way to reach across universes? Let's keep the conversation going. And if you enjoyed this deep dive into the mysteries of the cosmos, consider liking and sharing this video. The more we explore, the closer we get to uncovering the truth. Until next time. Keep wondering, keep questioning, and never stop exploring the infinite possibilities of our universe.